And we have some disagreement. We have a little over half of us saying that the two currents are equal. Some of us are saying that, well, light bulb's bright, right? So clearly you got to have more current at A than you have at B, right? Because somehow that current's being used up some way to give off the light. Well, let's think about that. We have a certain number of electrons per second flowing into the light bulb. So a certain number of electrons move in every second. And then some smaller number of electrons come out every second. Where are the electrons going? They turn into energy. So electrons annihilate with protons or positrons or something in the filament, and they disintegrate and turn into energy. Is that what's going on? Right? Okay. What do we? Okay. So if electrons are going away, we either have to have a nuclear reaction going on, right, where electrons are annihilating and just turning into photons. Or if they're just directly just going away, if electrons are just actually leaving the system or being sort of directly turned into photons, then what would happen? Yeah, what conservation of what? Okay, so one is conservation of mass, right? We got to have conservation of mass and energy. And the other conservation law we have is charge. Yeah, conservation of charge, right? Because if electrons were just leaving, this thing would be getting more positive and more positive and more positive, right? And I don't think that's happening. You could probably test that if you had a little piece of, well, if you had a little piece of tape or a little shred of paper and put it near here, and you would see it eventually get repelled and repelled, right? Or if it were positively charged, or attracted if it were neutral or negatively charged. But I'll assert to you that it stays neutral. You can try it out yourself if you like. Okay, so we got a problem. The electrons can't just go away. They can't just accumulate. The only other option is they would accumulate, right? If they come in and stop, then we got another problem because, we have a continuous charge buildup. So the only possible option is that the amount of charge flowing in has got to be equal to the amount of charge flowing out every single second. That really stems from this idea of conservation of charge, plus the idea of we have a steady state. Nothing's changing with time. Okay, so the rate of charge flow stays the same. And this is something called the node rule. But it's really just an expression of conservation of charge plus the fact that we're in a steady state. Okay. You could think of this as sort of a conservation of current rule in that sense. And the node rule simply says that in the steady state, the current in has to be equal to a current out of a node. What's a node? Well, a node is just a point or any specific spot in the circuit. So if I choose this light bulb as the node that I'm interested in, then the current flowing into that node, the electrons per second flowing into that node, have got to be equal to the number of electrons per second flowing out of that node at any given time. Okay. The number of electrons flowing out of the battery per second has got to be equal to the number of electrons flowing into the battery at any given time. The number of electrons flowing into point B has to be equal to the number flowing out of point B at any given time. Okay, so that's a node is just a spot in the circuit. And we'll deal with more complicated circuits later, but it also has consequences if you have a more complicated circuit where the wires actually branch apart. So, for example, if you have a battery here and some circuit that looks like this, okay, and it comes back together maybe over here. So here is the flow of electrons coming out of the battery. We'll call that I1. And then here's a spot where the you have two branches in the circuit, and there's I2 and I3. And so by the node rule, what has to be true? Okay, they just split. What has to be true about the relationship between these three currents? I1 is equal to I2 plus I3, right? Pick that as the node. The total number of electrons flowing in has got to be equal to the total number of electrons flowing out per second. I2 plus I3 is the total current out. I1 is the total current in. Okay, so it works in more complicated situations as well. Now, those of you, it's natural to think that the current in is greater than the current out. This is actually a common first guess, and it's kind of a natural one to make because you think that something is being used up, right? The light bulb's giving off light. Well, it's not the current that's being used up. What is being used up, or in some sense? Okay, energy, right? Where energy is being given off in the form of light. What's delivering the energy to? The battery, right? The battery is a source of energy here. The battery is doing work, and we'll quantify that next time or next week. But so we're not getting something for nothing. Okay, we are converting energy stored in the battery into light that's being given off, but it's not the current that's being used up. Okay.